Hello everyone, my name is Luobin. This is my workshop 2. In this workshop, I will use an algorithm to help me develop a game strategy. The rule of the game is to shoot the target to get points. Each target has its own score. You can hit the same target more than one times. Victory can be achieved when the scores are obtained to meet the requirements. A player can score 5 or 10 or 20 or 30 points in a game when hitting the target, assuming 50 points are the goal. This workshop is finding the number of ways to reach the goal. Here is my input and output. Given a total score n, my input will be n equals to 50, and given an array which will contain all possible target value, 5, 10, 20, 30. My expected output will be 16, which means there are 16 ways to reach 50 points by using these 4 values. So here I have listed all possible combinations of answers. You can pause the video if you want to take a look on it. For this problem, we are going to use an algorithm called recursion. Recursion is made for solving problems that can be broken down into smaller, repetitive problems. It is especially good for working on things that have many possible branches and are too complex for an iterative approach. For the question we are discussing now, as you can see, we are looking for every possible answers. Recursion works well for this type of question because you can search multiple branching paths without having to include many different checks and conditions for every possibility. So how well this works? For every target, we will have 2 options, either to include the target or not. When we include the target, we added its points to the current sum. If not, then simply move to the next target. Let's check the code. Here are the recursive code. And as you can see, checking this part, if your goal is less than 0, then no solution exists, return 0. If your goal is equal to 0, there is one solution, which is not include any targets, return 1. If there are no targets hit by n is greater than 0, then no solution exists, return 0 here. So the last line right here, it represents the recursive case. Return count sum of solutions including last target value plus count sum of solutions excluding last target value. Actually, the time complexity for recursive is not good because many subproblems are being called more than one time. It will cost too much time. How? So let's draw a recursive call tree, and it will show you why it will cost too much time. It would cost too much time. This diagram shows the recursive calls made in the execution of the program. And as you can see, we have everything at the first level. And you could choose either to include it or exclude it. Clearly, in the recursive method, the algorithm is unnecessarily calculating the same subproblems multiple times. As you can see right here, the function count 5, 10, 30 is called 2 times. If we draw the complete tree, then we can see that there are many subproblems being called more than once. By analyzing that diagram, we can see that time complexity for recursive is going to be the 2 to the power n, where n is the number of targets, which is pretty bad. So is there any way we can solve this problem in an efficient way? Actually, there is a method called dynamic programming can fix it. Jump to dynamic programming method. To save time and avoid solving the subproblems twice, we will use the dynamic programming method. It is a technique used to boost the running time of some algorithms where there is a potential for subproblems to overlap and use per-computed results. Therefore, the basic idea is we will use a 2D array like a memory table to store the subproblem solution. In this problem, we will use a bottom-up algorithm, which means it will start from the beginning, while a recursive algorithm often starts from the end and works backwards. Here is the memory table. We can begin from the column 1. You can see here that the index is 0, which means 0 points are the goal that you need to achieve. And checking the second column, you can see the index is 10, which means 10 points are the goal that you need to achieve, and so on. And let's check in the row here. In the row 1, the index is 0, which means no target hits. And checking the second row, the index is 1 right here, which means by hitting the 5 points target, there are 1 way to achieve the 10 points goal. And checking the third row, the index 2 right here, which means by hit 5 points target and 10 points target, there are 2 ways to achieve 10 points goal. So for example, if you check R3, C3, let's check R3, C3. You can see the index is 3 here. So which means there are 3 ways to achieve 20 points goal by hit 5 points target and 10 points target. Same thing here, if you check R5 and C6, which the index is equal to 16, which means there are 16 ways to, there are 16 ways to achieve 50 points goal by hit, 5 points, 10 points, 20 points, 30 points target. And this is the number we were looking for in this problem. So actually, you should think that we have stored every subproblem's answers, solutions in the table, so we won't need to calculate it again if we need it. Here are the illustration of the table. If you don't understand the table, and you can pause the video and check the table with this. And jump to the code of the dynamic programming and checking this part. If the goal equals to 0, then just return empty site to make the change. And if no targets given, 0 ways to change the goal. You can see right here, we have a solution table, which means we will store every, just like I said, we will store every solutions in the table, so we won't need to calculate it twice. Checking the second part of code and check if the value is less than the goals needed. Here we reduce the goal by target value and use the subproblem solution and added the solution from top to it. Here we just simply copy the value from the top. By analyzing the table and code, we can see that time complexity for dynamic programming is P times N, where P is the number of the targets and N is the total points of the goals, which is much better than the recursion. And it's pretty good actually. So it fixed the time issues, makes the algorithm more efficient. All right, so in the part of proof of correctness, I have run both recursion and dynamic programming on this platform. It shows the output, all of them are equals to 16. And there's one more thing, if you, as you can see here, is the time taken. For recursion, the time taken is equal to 0.09 seconds. And for dynamic programming, the time taken is equal to 0.06 seconds, which means it's kind of proved my idea that dynamic programming is it's better than the recursion. It saves some times. As long as you have a large value to input in the future, it will save more times. All right, so I think, yeah, I think that's all I have for this. And here is my references. All right, thank you.